Hello class. Today we discuss our new chapter which is strain energy, and here is the principle. When an elastic body, there is an external force acts on a body, and it will deform. If the elastic limit of the material is not exceeded, the work done in straining the material is stored in the form of internal strain energy or resilience. Okay, by and this external work done and this external work done by and applied load is equating to the internal strain energy stored in the body. Then this equation we because of this equation we obtain a method of determining deflections that is based on principle of conservation of energy. Suppose there is a pin jointed structure. When the member are in tension or compression, the energy stored depends on a direct force only. However, in beams and frames having rigid joints, shear stress and bending stress may also occur at any section, and the total strain energy stored depends on the magnitude of direct force, shear, and moment. While analyzing statically indeterminate structure, the work done by direct and shear force is neglected as compared to the bending. Before discussing the various strain energy theorems, let us first derive standard expression for strain energy stored in linear elastic system. There is a strain energy in linear elastic system. First case, there is axial loading, that means in pin jointed structures. Let us consider a straight bar L having a uniform cross sectional area A. If an axial load P is applied gradually and the bar undergoes a deformation delta. Suppose there is a bar, here is the length and the cross sectional area A, and it goes deform to delta L. Suppose delta L. Okay, it will deform to delta L. The work done is stored as strain energy U in the body will be equal to average force, which is equals to average force into delta, or area under the load deflection or load deformation diagram, which is called a strain energy. Half 0 in the initial is 0, and load is applied is gradually, so plus P 0 to P, हाफ पी इंटू डेल्टा, एंड डेल्टा किसी भी स्टेट बार में हम जानते हैं डेल्टा क्या होगा, पी एल बाय ए ई. डेल्टा एल इक्वल्स टू पी एल बाय ए ई, तो इतना हो गया हाफ पी स्क्वायर एल बाय ए ई. एंड द बार, इफ द बार इज वेरिएबल एरिया, दैट मीन्स एरिया विल चेंज with its length, then we use du equals to pu square dx by 2x e. Okay, now the total strain energy U, there is a 0 to L length, then the formula is P square dx by 2x E. This is total strain energy for the axial loading. Now the flexural loading, where again consider a member of length L subjected to uniform loading moment M and an element of length dx. अब moment अब हमारे लोड में, that means deformation is called a deformation in the slope, that means change in slope of the element due to applied moment. If m is gradually applied, u equals to m is gradually applied, so m half 0 to 0 plus m into di means change in slope, half m dot m by ei dx. How it will get di by dx, I know I क्या होता है dy by dx, then differentiate तो d2y by dx स्क्वायर. तो हमें वैल्यू चाहिए di की, तो m d2y by dx हम बेंडिंग इक्वेशन जानते हैं क्या होता है m by ei, तो di equals to m by ei dx. if you put is there, then du equals to half m square ei dx. टोटल एनर्जी क्या हो जाएगी 0 to L m square by 2ei dx. Okay, there is some standard expressions. Now the Castigliano's first theorem. Castigliano's first theorem, The concept of elastic strain energy can be very useful in the study of deflection of various points of structure under load. Now, the Castigliano first theorem states that the deflection caused by any external force is equal to partial derivative of the strain energy with respect to that force, mathematically expressed as du by dw equals to delta. W equals to delta, and in terms of moment du by del m equals to theta. Now the deflection of beams by Castiglio's first theorem. हम इसमें एक कंडीशन याद रखेंगे कि जिस पॉइंट पे हमें डिफ्लेक्शन पूछा गया है या स्लोप पूछा गया है तो हमें उस पॉइंट पर ही लोड होना चाहिए. अगर लोड नहीं दिया हुआ है उस पॉइंट पर तो हम उस पर एक इमेजिनरी लोड एक्ट कर सकते हैं. If a member carries an axial load, if member carries an axial force, then U equals to, we see standard derivation or a standard expression, then U equals to 0 to L P square dx by 2AE. P is axial force and the function of W1, W2 and so on, which is act on the body. From Castiglio's theorem, तो डेल्टा वन के रिस्पेक्ट में जिस पोजीशन पे डेल्टा वन रहेगा वहां पर हमारा डेल वन, एंड डेल्टा टू जिस पोजीशन पर रहेगा तो वहां पे हमारा डेल टू. ओके, डेल यू बाय डेल टू, डेल डब्ल्यू टू. Strain energy due to bending. Now from bending, then equation, standard equation is 0 to L m squared by 2ei dx. M is the function of w, so del u by del w1 del w, or and it is depend on the w2, so del 2 is equals to del u by del w2, and also the slope is changes, and theta 1 equals to del u by del m1 is the m1 is the function of m. Now we solve some questions, numerical problems. Calculate the central deflection and the slope at ends of a simply supported beam carrying a UDLW per unit length over the whole span. क्या दिया हुआ हमारे को हम क्वेश्चन में कि एक सिंपली सपोर्टेड बीम दी हुई है जिसके ऊपर UDL केस लगा हुआ है और सेंट्रल डिफ्लेक्शन हमने पूछा है. सेंट्रल डिफ्लेक्शन एंड द स्लोप, स्लोप एट द एंड्स. सेंट्रल डिफ्लेक्शन पूछा और स्लोप वैल्यू पूछी है. तो सेंट्रल डिफ्लेक्शन पूछा तो हम क्या करेंगे, सबसे पहले एक इमेजिनरी या फिक्टिशियस लोड हम एक्ट करेंगे सेंटर पे, जो कि हमने W से इंडिकेट किया हुआ है. देयर इज अ साइन कन्वेंशन फॉर मोमेंट. इफ वी goes from right to left, so anti-clockwise moment is taken as positive, and if we goes left to right, so clockwise moment taken as positive. Now from the figure reaction, we calculate reactions at A and B. Then RA is equals to, there is a UDL, then WL by 2, and at the center is W acting, imaginary load W acting, then plus W by 2 for RA and RB. RA expression is WL by 2 plus W by 2, and RB WL by 2 plus W by 2. Now from Castigliano's first theorem, del deflection at center equals to del u by del w, because we find out deflection at center. Now we consider a load on that point and differentiate of strain energy with respect to that load. It will gives the deflection at the center. Del u by del w equals to 1 upon ei 0 to L mx del mx by del w dx. Now mx is finding out from this equation. We consider at x distance from A, RA into x, which is clockwise direction, and B goes from left to right, that it will clockwise, so it is positive. RA into x and W is negative, then minus W x dot x by 2, that is mx. There is expression of for mx, and mx is the differentiate with respect to W, and the mx differentiating with respect to W, then we get x by 2. And now that central deflection, we goes from figure, there is a strain energy is equating from both the direction, from A to center and B to center, that is up to this L by 2. So it will 0 to L by 2, and the equation is same for both the directions. There is a 2 by ei, so that's why it's 2 by ei. Now multiply by x by 2 in this equation and put W is equals to 0. That means it is the imaginary part, so it will not act on the body or act on the beam. So W equals to 0. Then we will get this equation, and the integration of x square is x cube by 3 and 2 to the 4 and 3 12 minus and x cube का इंटीग्रेशन होता है x की पावर 4 by 4 and 2 to the 4 4 4 16 0 to L by 2. We will put these upper limit and lower limit in this part, so we will get this equation, and central deflection is 5 by 384 5 by 384 W L power 4 by EI. Okay, now for slope, now let us assume a clockwise moment at A. There is an imaginary moment, so we find out slope at A. Now the reaction at A and B, there is a W, so reaction at A is WL by 2 minus M by L. We calculate from the equations, take moment about RV, then we find RA, and RA equals to RB, RA plus RB equals to W into L, so it will positive. From Castigliano's first theorem, theta I equals to del U by del M, so 1 by EI 0 to L mx del mx by del M dx. Now mx, suppose there is a x, consider a x, then RB into x, which is positive because it will anti-clockwise direction and we goes from right to left, so it will positive. We seen in the sign convention of bending moment diagram, for sign convention for bending moment, fit, then mx equals to wl by 2 plus m by l into x, there is a positive, this is positive, and minus wx dot x by 2. Okay, now the differentiate mx, then dmx by dm equals to x by l. We will put this in equation, put this equation for 0 to L, and put m equals to 0 because there is m is imaginary, so we will get this equation, and now integrate this portion, we will get this value, theta a slope is WL cube by 24 EI. This is positive, so we can say that the rotation is clockwise in the direction of applying moment, imaginary moment. And there is complete question, and the second problem is, now in next problem, a beam of uniform section end of length 2L is freely supported by rigid supports at its ends and by an elastic prop at its center. If the prop deflects by an amount lambda times the load it carries, and if the beam carries a total distribution load, it will give total distribution load, not a UDL. W show that the load carried by the prop is 5W by 8 bracket 1 plus 6 EI lambda by L cube. There is a diagram A, B and C. There is a prop P. Assume the prop load is P and this is W. Let the prop reaction be P and the load on beam is W. Okay, then UDL is W by 2L, L plus L, that is per unit length. Now reaction at ends R and RB is half of W minus P because of symmetry. Now the deflection at the prop, delta C equals to क्या होगा, del U by del P equals to 1 by EI, because P is given in that case, so we not consider imaginary load. Then del U by del P equals to 1 by EI mx del mx by del P dx. Now P is acting upward, and the deflection lambda is gives downward, so it will negative, minus P by P minus P lambda equals to 1 by A integration of mx del P dx. For any section distance x from A, we consider a section x from A. Now the moment is Ra into x is positive and minus W x dot x by 2. This is the equation. Now the differentiate this mx equation with respect to p, then we get minus x by 2, and we will put this equation, this value in equations. And negative is common, minus and minus, we will cut that minus. In the remaining part is p lambda ei by 2 is equals to, then integrate this portion with this, we get this equation, and now simplify this equation, and we will get, yes, this simplify the equation. Now wl cube and wl cube by 32, now we get 5 wl cube by 96 minus pl cube by 12, then equation is goes this. Now it is proof. There is a simplification of equations. Now we get the p equals to 5w by 8 1 plus 6 lambda ei by l cube. Okay. Now the another question is there. A steel tube having outside and inside diameters of 10 centimeter and 6 centimeter respectively is bent into the form of a quadrant, the form of a quadrant of 2-meter radius, and end is rigidly attached to a horizontal base plate to which a tangent to that end is perpendicular, and the free end supports a load of 1000 Newton. Determine the vertical and horizontal deflection of the free end under this load. The dimension of the cross section may be considered as small relative to the radius of the curvature. Okay, take E equals to 2 into 10 power 5 Newton per mm square. From the figure, there is a quadrant. There is a quadrant. We suppose a ds element and the slope d theta and radius r. There is a w load which is act on free end. Okay, from first case vertical deflection of end A. So at end A there is a this is A, this is point A and D. Then at A there is a vertical load W, so we are not may assume a load. So then delta AB equals to del U by del W equals to 1 by EI M del M by del W ds. Here M, there is R, there is slope theta, so there is theta, so we calculate there is a portion of r sin theta and r cos theta. Is this portion is r cos theta, and this portion is r cos theta, this is r cos theta, and this is r sin theta. This portion is r sin theta and this portion is r cos theta. So m equals to load into perpendicular distance, then w into r sin theta, which is clockwise, and we goes from right to left, then it is negative minus wr sin theta, and we differentiate with respect to w, we get minus r sin theta, and ds is equals to r d theta. Okay, r equals to angle into radius or radius into angle, so ds equals to r d theta, and limit is goes from 0 to pi by 2 in quadrant. So delta AB, we put these values, minus WR sin theta minus R sin theta R d theta, then WR R, that means WR cube in 1 by I. Okay, minus minus plus, then sin square theta. We cannot integrate sin square theta, so simplify sin square theta, which is equals to 1 minus cos 2 theta divided by 2 d theta. Then 1 by 2 is theta by 2, and cos 2 theta is sin 2 theta by 2. So sin 2 theta by 4. We put the limits, upper limit minus lower limit, so we will get 1 by ei wr cube pi by 4. Now the value of I and value of E. I is pi by 64 10 to the power 4 minus 6 power 4. It is in centimeter power 4. We convert into mm, and EI is the value of 854 into 10 power 9 Newton mm square, and the radius is 2 meters, so 2000 mm. And then put the values, and we get 7.35 mm in vertical direction. Now second is horizontal deflection of A. And so in the diagram, in the question, there is no horizontal force given in the question. So we assume a horizontal force at point A is H. There is imaginary horizontal load H as shown in figure. Delta H is del U by del H 1 by I M dot del M by del H ds. M is, so M on that section is W r sine theta, which is negative, and minus H, there is r cos theta is this position. Now we find out these values. Is total length is r, and this portion is r cos theta, and we find out this value is r minus r cos theta. So H into r minus r cos theta. So the value is, the equation is minus W into r sine theta, is W is load which is given in the question, and minus H r bracket 1 minus cos theta. Okay, now del M by del H, which is constant for this value, then it is 0 and H is 1, then remaining part is minus r 1 minus cos theta. ds is equals to r d theta, and limit varies from 0 to pi by 2. Put in the equation and put H equals to 0. So remaining part is W r cube sine theta 1 minus cos theta. Put in this equation and integrate this part. Then we got sine theta and cos theta. So we multiply by 2 and divide by 2 in this portion. In this portion we multiply and divide by 2. So sine 2 theta by 2, and the integration of sine 2 theta is cos minus cos 2 theta by 2. Okay, and the limit 0 to pi by 2, we put the limit, upper limit minus lower limit. So cos pi by 2 is 0, and cos pi is minus 1, and cos 0 is 1. Then the value is this, and put the values of ei and w and r. The horizontal deflection is 4.68 mm. Thank you.